Good afternoon, everybody. Let's begin today's class. Today's class begins our chapter 2 or topic 2 or session 2 of experimental design 1. That is STA 3108. So for those of you watching from any part of the world, my name is Dr. John Effiong Hussein, and I welcome you to my class on experimental design 1. This is Genesis Educational Research Hub, GER Hub. So please join us as we begin. So we shall be discussing the second topic in STA 3108, precisely experimental design 1. That's the course title for this course, and this is the course code as I have it in our school. And our topic 2 is completely randomized design. Completely randomized design. I believe I told us that in the last class, right? Did I? I believe I did. So now we've moved away from our introduction to experimental design, where we discussed what experimental design is made up of, in terms of experimental design being one part being design of experiment and the other part being analysis of what? Experiment. And we discussed several things. Let's begin with answering the question. I would call this, if I were you, I would call it 2.1, where we shall answer the question, what is a completely randomized design? So let's start from there. And please going forward, we'll be calling that design CRD. Okay? So what is a completely randomized design? If you tell somebody that you study completely randomized design in today's class, they may want to know what it is by definition. Okay, so in today's class, we'll start with the definition and we'll explain what the definition means. Is it clear? So let's start with answering that question. Quickly, we would say a completely randomized design, a completely randomized design, CRD, is an experimental design technique, or experimental design in which the order of experimentation, hope you can see the board clearly, in which the order of experimentation applied to several treatments, is completely random. It's completely random, so that the experimental units are considered homogeneous. Okay? So everything we shall say going forward in today's class will border around this definition. Is it clear? So question is, what is a completely randomized design? A completely randomized design, the acronym for it is what? CRD, completely randomized design. Is what type of design? It is an experimental design to start with. There are so many experimental designs, okay? It is an experimental design in which the order of what? Experimentation applied to several treatments is completely what? Random. Is it clear? Now, if you remember our class yesterday, or in case you watched the video of yesterday's class, you will see that we recalled that under factors come levels we call treatments. And in each level called treatment, there are also what? Levels of observations we call replicates. Is it not so? Now, we are saying that what is called a completely randomized design is a design in which those experimental units or observation in a certain treatment are what? Applied randomly. That is, they are completely what? Random in nature. What it means is this. For instance, let's assume that the four of you in this class, the weights of the four of you are to go into what we call treatment 3. That is for 300 level students. There are 4 treatments. Treatment 1 is for 100 level students, the weights of 100 level students. Treatment 2 is the weight of what? 200 level students. Treatment 3 is the weight of what? 400 level students. And treatment 4 would, of course, be the weight of 400 level students. Now, what we are saying is that if the way you take the weights of the 4 persons that make up the 400 level class is completely random, meaning that I don't have to start with any order of taking him first, this one second, pegging you at third, and Deborah fourth. No, I can pick anybody among the 4 of you at random and take your weights, which goes into that particular treatment. That is treatment 3. Then it means that we just might be having what? A completely randomized design. That's why we are saying that it is a design, it's an experimental design in which the order of experimentation applied to several treatments is what? Completely random. And what that does is that if the order of of experimentation applied to several treatments is completely random, as by implication, it means that the experimental units will be what? Considered homogeneous. Okay? Now, let's move on to something concrete. Let's move on to something concrete by saying the following. So, based on this, let's move further to say, suppose we have A, or let me use B. Suppose we have B levels, okay? B levels of a single no, let me use A, okay? Suppose we have, it should be have, suppose we have A levels of a single factor. What would that mean, class? What would that mean? When I say suppose we have A levels of a single factor, what does that, what am I trying to say? It's another way of saying what? No. You don't seem to be getting my point. Suppose we have A levels of a single factor. What does it mean? A single factor called weights, and we have 4 levels of this factor. What does it mean? Level 1, level 2, level 3, level 4. What does that mean? It's another way of saying I have 4 treatments. Is it not so? So, suppose we have A levels of a single factor, means suppose we have A treatments. You understand me? Because this is the factor itself, weight. The levels of this factor are treatments. You get me? So, me saying, suppose we have what? A levels. In this case, your A is what? 4. Suppose we have 4 levels of what? A single factor such as weight. It's the same thing as saying, suppose we have what? 4 treatments. Huh? So suppose we have A levels of a single factor that we wish to do what? To compare. That we wish to compare. So the comparison could be, when we say compare, the comparison could be, look up everybody. The comparison could be, you will take, if X1 represents the weight of year 1 students, X2 represents the weight of year 2 students, X3 represents the weight of year 4 students, and X4 represents the weight of final year students. That's 400 level students. Now, I'm going to have weights here. I'm going to have weight here. I'm going to have weight. Now, the question is, the interest of a completely randomized design may be the comparison of these weights. Are the weights from 100, 200, 300, and 400 significantly different, or are they what? Not significantly what? Different. And that's what we mean by what? Compare. We wish to compare what? There's the treatment. Suppose we have A levels of a single factor that we wish to do what? Compare. So we may want to compare whether the weights coming from these 4 classes are significantly different or not significantly what? Different. Is it clear? So what happens in that instance? The different levels of the factor, the different levels of the factor are often called treatments. I believe we've already taken the definition on treatments previously. Is it not so? Are often called treatments. Now, the observed response from each of the A treatments, the observed response from each of the A treatments is a random variable. Please, is that true or false? Is that true or false? Why is it true? It's not just saying true. Why is it true? It's true because it is true. Or it is true because I said it. We are saying that, see, look up. I don't want you guys, see, I never would like students writing without understanding. You get me? Now, look at it again. I have made reference to this diagram severally. Look at factors. One factor in this case, I'm still using my reference example as weights. Under factors come the following treatments. I'm still using X1, X2, X3, X4 as the treatments. So, now, what is being said here, this statement you've just written, is saying that the observed response from each of the A treatments is what? A random variable. What are the responses? There are 5 guys in year 1, and their weights, you have to take them. As you move from guy 1 to guy 5, the weights are changing. And the weights that are changing are the values assumed by X1 in accordance with a given probability value. Looking at this now, X1 is a random variable because it will assume values you call responses from all the students in that particular class. As you measure from student 1 to student 2, student 2 to student 3, all the students that make up the ones in year 1. Treatment 1 is for year 1, the weight of year 1 student. This guy's weight cannot be this guy's weight. His weight cannot be your weight. Each point you take, the weight will give a different value for what? X1. So at one point, X1 would assume X11. It will assume X12. It will assume X13. It will assume X14. If there are 4 observations in this group, this will be, all of them here are observations in treatment 1. Do you understand me? They are all observations in treatment 1, but this is the first weight observed in treatment 1. This is the second weight observed in treatment 1. This is the third weight observed in treatment 1. This is the fourth weight observed in treatment 1. All of them that were observed in treatment 1 are values under this what? Under this variable. And it makes this variable a what? A random variable. Is it clear? Now, if you move from treatment 1 to treatment 2, you would also have values x2. X2 values assumed by what? By the random variable x2. And this will be x21. The first students whose weight you take in what? In treatment 2. The first 200 level student whose weight you take is what? X21. X22 will be the second 100 level students whose weight you take. X23 will be the weight of the third second 200 level what? Student. And this will be what? The fourth weight of a 200 level what? Student. Do you understand me? All of them here are different values assumed by this what? This random variable. Is it clear? So when we say that the observed response from each of the A treatments is a random variable, it means that x1 is a random variable, x2 is a random variable, so also is x3 and what? X4. Is it clear? So please don't just write line by line, understand what we are writing. Am I understood? Because we are moving somewhere with this development. Is it clear? Okay, so let's I hope we can proceed. So next thing is a statement. So the data setup for this instance will be, so we put below, I would love to use a horizontal setup. So see what I'm going to do. I'm going to put here, are you seeing? I'm going to put here factor. Okay? Now, under factor, I'm going to put, what do you call it? So I'm calling this my factor what? X. Okay? For instance, I'm calling my factor X. I'm going to do this. Then I'm going to call this here. These are what? Treatments. Under my factor. And let's assume we've already said we have what? We are assuming we have how many treatments? 8 treatments, right? So I'm going to put here, let me reserve this for levels. Huh? Let me reserve this for levels. So I'm going to call this levels. So let me reserve this for levels. Now see what I'm going to do. This will now be, let's start with 1. This is treatment 1, okay? Treatment what? 2. Treatment what? 3. And it goes down to how many treatments? Treatment A. We are considering A treatments. You see it? Now, underneath the levels, let me bring levels here. Let me bring levels here. Okay? Now for levels, I have what? For levels, I'm going to have, let me put these doubles, So for levels, I'm going to have level 1, level 2, level 3, up to, I want us to consider having B levels. Do you understand me? I want us to consider having B levels. So there are A treatments and what? B levels. Now, in this instance, saying that we have B levels, what does it mean, everybody? What does it mean to have B levels? If you follow what I'm explaining, what does it mean to have B levels? Huh? Experiment, how many times? B times. Thank you very much. It means that in this case, I am assuming that in every class that makes a treatment, there are B students to take B observation from. You understand me? But please take note, in a completely randomized design, that is not always the case, because in reality, year 1 students, the number of year 1 students cannot be automatically equal to the number of year 2 students. You understand me? So, but in this instance here, my first assumption is that we have equal number of observations taken from each what? Class. Is it clear? So what I'm using is, this setup I'm using for my data is what we call the horizontal setup. In the horizontal setup, the treatments are put horizontally. The levels are, that is, the levels are placed vertically and the treatments are placed horizontally. You understand me? This table can be swapped such that treatments can come here and levels can come here. That will be a vertical setup because our eyes are fixed on what? The treatments. Is it clear? Now, look at it. So if there are B levels but A treatments, it means that you should take, for instance, look at what I've just done. X is the factor. And since X is a random variable, it means that all the values assumed here, all of them will be what? X. All the values will be X. You get me? But the difference will be their positioning. The difference will be their positioning. Is it clear? So this will be X, 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 X. I hope you understand what I'm saying. All the values will be X, 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 X. So also will this be X, X, X. This is my, I'm bringing my vertical ellipses here. And this will be what? X, 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 horizontal ellipses, then X. Now, what am I trying to do? I am just making you see that because we have said our factor is X, whatsoever X means, all the values assumed by X will be what? Small x. There are A treatments here and what? B levels. Now, let's now make our values different. So this X here, the convention I'm using is, I'm using treatment before levels. You get me? So every variable, this is the every value that is here is found in treatment 1. You see it? So I'm going to put here 1, 1, 1, 1. Every value found here is found in what? Treatment 2. So I'm going to put here 2, 2, 2, up to what? 2. I hope you follow me. So also would this be what? 3, 3, 3, because they are all values taken in treatment what? 3. Then this will be what? A, up to what? A. You see it? So now if you go into each treatment, you will now notice that this value here is different from this value. Even though all of them are values taken in treatment 1, this one is the first observation taken in treatment 1, so we put what? 1. This one is the second observation taken in treatment 1, so we put what? 2. This is the third, so we put 3. And this is what? The bth observation. Okay? This is the bth what? Observation. So we put here x1b. So x1b now means the bth observation taken in what? Treatment 1. So the same thing goes for this. This will be what? 1, 2, 3, up to what? B. That will now become the what? The bth observation in what? Treatment 2. This will be the third observation in treatment what? 2. Is it clear? This will be 1, 2, 3, up to what? B. And this will now be what? 1, 2, 3, and this will be what? AB. Is it clear? I hope you follow. Now, the first question the student will be asking is this. In a setup such as this, where all the levels are equal, what will be the total number of values we have observed? The total number of values will be what? AB. Is it not so? The total number of values will be what? AB. However, if this is an unbalanced setup such that the number of observations in treatment 1 were not the same as the number of observations in treatment 2, this B here, we will put an index to it such as let's say BL, where L will assume values from 1 to whatever value. You get me? So that in this one now, we can have B1, it will not be B1 up to B1 for the number of B1 will not be the observations in the number of observations in treatment 1. B2 will not be the number of observations in what? Treatment 2. Is it clear? I hope you follow me. So we are not using BL, means that by default we are assuming that all our observations are equal in each treatment. Another thing to take note of is this: when we start going for unequal treatments, we won't be using AB. You will be wrong. Let me show you something. Please point the camera this way. Look at this, everybody. See the difference here. Let's assume that we have three. Look at this: 3, 4, 5, 1, 2, 6, 2, 4, 3, 7, 1, and 8. If I ask you, you will notice that in this setup, how many? This is like a matrix of 3 by 4, making 12 compartments. Is it also? And the 12 compartments are completely filled. If I ask you, how many numbers do you have in all the compartments of this matrix setup? You will tell me 12. Am I right or wrong? But if it so happens that you are looking at this as treatment and looking at this as levels, there are 3 treatments, 4 levels. Now, let's assume that in this treatment, you had only 3 values. And in this treatment, you had what? In the first instance, when all of them were complete, you won't be wrong to say that there are 3 by 4, which is giving you what? 12 observations in that setup. That is the case we are dealing with, where you can boldly say the number of data entries in the setup is what? AB. But when it is incomplete, you will be wrong to say it is AB. In that instance, we will no longer be using AB, we'll be using what? N. Where N will stand for the total number of observations, in which case you have to actually do what? Count. Or you have to take B1, the number of observations in what? Treatment 1, plus B2, plus up to what? BA. And that will give you what? N. I hope you understand the difference. So that is what I want you to take note of. Let's proceed. Are you done writing this? Eh? But I can wipe this off, right? Now, okay. So, let's write there in. Let's call this, please. Let's call this table. Let's call this table 1. Okay? Let's call that table 1. So I'm going to make a remark here. In table 1 above, the setup for the data implies that there are a total of AB observations. Let N be the total number of observations. Let N denote the total number of observations. So if we use N to denote the total number of observations, then what will happen? If the total number of observations is AB, it means that N is equal to what? AB. Is it clear, everybody? This is because in each treatment, the assumption is that there are equal number of what? Number of observations or levels, yes. Observations or levels B. Is it not so? However, in table 2 below, this is not the case, as the total number of observations in each treatment is BL, where L equals 1, 2, 3 to what? A. Hence, N will be equal to B1 plus B2 plus B3 plus up to what? BA. Is it clear? So let's, have you written this one? So what I want to do now is I want to alter this table. So what we are going to do, when it is unequal, I'm going to call this down table 2. Are you seeing it? And the only difference will now be, I will put here BL. You see it? And this will now be X1 B1. You see it? And this will be X1, X2 B, B2, X2 what? B3, X2 B, and XA B what? BA. You see it? I hope you follow. Good. So now the next thing I want us to look at is the model. So the question now is, what is the model? What is the model for a completely randomized design? Now, please take note of one thing. Please take note of one thing, that a completely randomized design is the same in some aspect as a one-way analysis of variance. A one-way analysis of variance is also called a one-factor analysis of what? Variance. And what makes a completely randomized design comparable with a one-way analysis of variance is because both of them use what? One factor. Is it clear? There is one factor under which we consider several what? Treatments. Okay, are we there? Now, so don't write this one above. So it means that for the case of an unbalanced setup, what would you have? We would have what? Table 2. You see it? We will end up having table 2. So in table 2, you can't tell us that N, your N is not what? A times B. Is it clear? Your N will be the sum of what? Each levels. So let's proceed. Now let's discuss the model in CRD. Okay? The model in what? In CRD. Are we there? Now, the linear statistical model, for a completely randomized design is given by Yij equals mu plus tau I plus, okay, so the model is given by Yij equals mu plus tau I plus epsilon ij. Okay? Do you understand me? So this is the model for a completely randomized design. And if you go into one-way analysis of variance, you'll notice that this is the model for a one-way analysis of variance. Now, let me end this class here with telling you something. I'm going to tell you why. Let's can I wipe this table off? It's the same table, only you change that stuff. Now, please look up. This is just by the way. Are you listening? So this is what I want you to know. You see, if you ask a student, what is the model? Let's call this in particular equation 1, because I'm going to be having several of these equations. Please listen. Just drop your pen and listen. Now, if you ask a student, how did this model come about? They will tell you they don't know. And most students will tell you that the model is what it is. So it's a case of it is what it is. Huh? That's how they got the model. But the truth is this. So for you to get this model comes from the fact that there is what do you call it? A gap between the observations and what is called the treatment means. Okay? That amounts to error, and that gap is what prompts this model. So for now, I'm going to show you how the models are obtained. This model here, I can ask you in your exam to give me the model in terms of the grand mean, and also ask you to give me the model in terms of the treatment mean. So this is just one out of the two. Is it clear? So for a completely randomized design, the model is this linear statistical model, which I can tell you for sure when you start doing analysis of variance 1, you'll come to realize what I'm saying. It is the same model for what do you call it? A one-way ANOVA. Is it clear? So we are going to stop there, and we will continue this class in our next meeting. Okay? So thank you very much. Is there any question? Is there any question? Yes, virtue. Debbie Smile's question is smile. Yes. I'll show you in the next slide. I'll show you in the next slide. Huh? Or do you want me to show you now? See, look at this one you memorize. This one you memorize, you are just wasting your time. Let me show you what happened. Now, what we call the model is what is actually happening in the data setup. So this is what we do. We call this, we say mu I is the treatment mean. So this I here can take values from, of course, I can take values from 1 to what? 1 to A. Because there are A treatments. Is it clear? Now, each treatment has an observation. Is it not so? In each treatment, there are a number of observations, in particular B observations, if you are considering all of them to be equal. So, if you want to start talking about the model, I am saying you don't need to memorize. See where the model begins. This thing came from somewhere. This is where it came from. It came from the difference between the observations and the treatment mean. The treatment mean gives you this error. That's where it begins. Is it clear? So if you now make Yij the subject of formula, what are you going to get? You are going to get mu I plus what? This model, this is the original model. This model is what you call the model for a completely randomized design in terms of the treatment means. Do you understand me now? So this is what I should have even called my equation 1. Now, how did this model come about become this? Do you understand me? Now, this one, the model, the very first model came as a result of what? Taking the discrepancy between the observations in each treatment and their respective treatment means. Now, the difference between any observation and the treatment mean gives you what? An error. An error of the error term here. Now, this mu I here mu I. If you subtract all these mu I from the, if you subtract them from the grand mean, it will give you tau I. This tau I is called the treatment effect. The treatment effect is obtained when you take away the treatment means from the respective, they are from the grand mean. You know, all of them have, if you average all the treatment mean, it will give you the grand mean. Or if you average all the observation in the data set of it, will give you the grand mean. Now, if you take the discrepancy between each treatment mean and the grand mean, it will give you what? Tau I. Now, if you now make mu I the subject of formula, what are you going to have? You have mu plus what? Tau I. Now, take mu plus tau I and replace it here. What would you get? You see it now. That's why I'm telling you that the student should not cram or memorize. Once you remember that it starts from here, you will get this. Is it clear? Thank you very much. We'll continue from there in the next class.